Welcome to The Explainer. Today, we're taking a trip about 150 light years from Earth to the Hyades star cluster to investigate a massive cosmic mystery. We're going to look at one of the most fascinating disappearing acts in the entire universe. Now, if you look up at the constellation Taurus, you'll see the Hyades. It's this prominent group of stars that has completely captivated astronomers for centuries. But as it turns out, the Hyades cluster is actually a massive crime scene. And today, we're stepping into the role of cosmic detectives to figure out exactly what went down there. See, scientists are quite literally looking for missing bodies in space. Dead stars, to be exact. The fundamental rules of stellar evolution tell us exactly how many dead stars should be sitting in this cluster right now. But when we actually look, a significant chunk of them are simply gone. So how did 21 stars, and we're talking incredibly dense, incredibly hot stellar remnants, just vanish without a trace? Okay, let's dive into this. 400 million. That represents a glaring gap in the timeline of the Hyades cluster. You see, the cluster itself is estimated to be about 700 million years old. But when astronomers went looking for the oldest white dwarf, which is just the glowing, dead core of a star that's exhausted its nuclear fuel, well, the oldest one they could find had a cooling age of only 300 million years. That leaves a massive 400 million year gap. So where are the older white dwarfs that should have formed during the entire first half of this cluster's life? Section 1. The Hyades Cluster Mystery. Back in 1992, a paper published in the Astronomical journal really launched this whole cosmic investigation. Our lead detectives are a team of astronomers, Volker Weidemann, Stefan Jordan, Iko Eben Jr., and Stefano Casertano. They were looking at the data on the Hyades cluster and realized something was deeply, deeply wrong. They knew the cluster's age, and they knew the ages of the white dwarfs inside it. And by putting two and two together, they realized that a huge portion of the cluster's history was simply missing from the observational record. Let's walk through the forensic clues they laid out. First, the turn-off mass of the cluster, which basically tells us the mass of the stars that are just now dying, is about 2.25 times the mass of our Sun. Second, the star that died to create the oldest white dwarf we can find was about 3.0 solar masses. Now, based on standard distributions of star masses in the universe, there should be a lot of stars that started with masses between 3 and 8 solar masses. They would have died even earlier, leaving behind older, dimmer white dwarfs. The math says there should be at least 21 of them. But here's the kicker. Absolutely zero are currently found in the cluster. Not a single one. Section 2. Where are the missing dwarfs? To really understand this, we need to think of a star cluster kind of like a leaky bucket. As the cluster orbits the galaxy, it's interacting with the gravitational forces of nearby stars and gas clouds. These tidal forces essentially eat away at the cluster, causing lighter stars to evaporate or leak out over time. But here's the puzzle. The missing white dwarfs came from some of the heaviest stars in the cluster. So why are the remnants of the heaviest stars the ones going missing, while a bunch of lighter, main-sequence stars are still just hanging around? Now, what's really interesting about this is the sheer scale of what this cluster used to be. The researchers realized that to explain its current composition, the Hyades must have lost a massive amount of its original population. Today, it's got about 400 stars and a mass of roughly 300 suns. But initially, born out of a giant molecular cloud, it could have contained up to 5,500 stars with a mass of 14,000 suns. I mean, that wasn't just a leaky bucket, it was a total flood. Up to 90% of the original low-mass stars have already migrated out of the cluster. Section 3. The Great Stellar Evaporation. So here is the brilliant escape route detailed by the authors. Step 1. Because they're the heaviest, massive stars naturally sink right to the very center of the cluster due to gravity. Step 2. They exhaust their fuel, shed their outer layers, and evolve into white dwarfs. But here's the trick. They lose most of their mass in this process, dropping way down to a lightweight 0.63 solar masses. Step 3. During this violent death, probably due to an asymmetrical planetary nebula ejection, they get this kinetic kick that pushes them outward from the dense center. And finally, step 4. Now that they're lighter and sitting on the outer edges of the cluster, they just slowly evaporate into the wider galaxy over hundreds of millions of years. Section 4. Searching the supercluster. To actually find them, the authors investigated a prominent theory known as Egan's supercluster. Astronomer Olin Egan proposed that unbound stars retain a sort of memory of where they came from. Think of it like a group of people who all left the exact same party at the exact same time. Even if they aren't holding hands anymore, if you look at a city map, you can probably still identify them because they're all generally walking in the exact same direction at the same speed. Egan argued there was this massive supercluster of stars around our sun that all shared the Hyades cluster's exact space velocity, So the crucial point is, the authors combed through a catalog of 700 known white dwarfs to really put Egan's theory to the test. They narrowed that down to 30 potential candidates that seemed to be moving the right way, but when they applied strict tests, like requiring the stars to match the exact velocity and direction of the Hyades, only 9 reliable kinematic matches remained. This strict supercluster theory, where they all perfectly march in lockstep, didn't quite hold up to the data perfectly. But, they didn't stop there. When they mapped out where all of these dead stars were heading across the whole sky, they found a strong concentration of stars generally heading toward the exact same point in the sky as the Hyades cluster. So, okay, they weren't a perfect supercluster with identical speeds, but they were definitely part of a massive loose stream. In fact, when they ran the numbers, the best mathematical fit for what they were observing was a mixture. About 60% of the nearby white dwarfs are just random background noise, stars doing their own thing, moving in random directions. But an incredible 40% of them are part of this Hyades stream. 2/5 of these dead stars in our galactic neighborhood are broadly moving together, likely sharing a common origin. Section 5. The Galactic Needle. Let's move to and see how this builds, because when they ran the computer simulations, the results were just incredible. They compared the original cluster to the escaped stars. The bound cluster is this tight, dense sphere, maybe 9 to 14 parsecs across. But the escaped stars, they don't form a sphere at all. Because of the gravitational tides of the Milky Way galaxy itself, which is constantly pulling and stretching the space these stars move through, they get pulled out into this massive, stretched-out shape. It's a literal needle of stars drifting through the Milky Way. Just look at the dimensions of this needle. The mathematical models predicted that after 700 million years of constant evaporation, the escaped stars would form a structure 122 parsecs long. To put that into perspective, that is almost 400 light years in length. Yet it remains incredibly narrow, only about 10 parsecs wide. And because of the way galactic rotation works, this needle points at a slight 8-degree angle to the direction of its orbit. The math perfectly explained the escape route and the current location of those 21 missing dead stars. They're strung out in a massive needle passing right through our cosmic neighborhood. The authors actually end their 1992 paper with a truly mind-blowing thought. They wrote, "We wonder if Egan's supercluster and the stream which we find could be superpositions of similar needles deriving from clusters made successively by a common parent giant molecular cloud." Basically, what they're saying is that our galaxy might not just be a random soup of stars. It might actually be filled with overlapping, distinct needles of dead stars and planetary systems, all tracing their ancestry back to ancient, long-dead clouds of gas. Which leaves us with one final, awe-inspiring question to ponder. What invisible streams of dead stars are we drifting through right now? Every time you look up at the night sky, remember that you aren't just looking at isolated pinpricks of light. You're looking at the cross-sections of massive, ancient rivers of stars flowing through the dark. Thank you so much for joining me on this explainer. Keep your eyes on the stars and stay curious.